So, good morning, everybody. Thank you for attending to this coffee break. So, I'm ready. So, my name is Donald Picard. I'm an application expert at Eddyfi. So, today we'll talk about the PEC Advanced Analysis, focusing on the ship deck inspection. So, quick outline. So, we'll just introduce the presentation. We'll cover the summary of the PEC principles. I will just summarize the advanced analysis tools that we have access. Then we'll move on to the data analysis of a ship deck example, and we'll conclude the presentation if you have any questions. So as you know, the pulse eddy current is an advanced electromagnetic technique that is mainly used to detect internal and external corrosion in either the carbon steel or the cast iron components. It is mainly used to detect the volume loss under insulation, fireproofing, or any type of non-conductive and non-magnetic coating. And it is really important to remember that it provides a volumetric measurement that is always relative to the calibration area. And it is now captured by the few standards, so SME, ISO, and API. So the pulse eddy current is a proven inspection technique used to detect and assess the corrosion under insulation, but also under fireproofing. But it is really important to remind that to remember that it is a technique that can be used to evaluate any volume loss in any ferromagnetic material, mainly carbon steel and cast iron, under any type of coating that prevent direct access to the surface, so such as a ship deck. So in this example, we can see that this is a ship deck compartment covered with tiles, and by doing a PEC inspection, you can see on the C-scan in the figure of the middle here that we detected few wall loss indication. And by removing the tiles, we confirmed that there were a quite severe corrosion under the tile. So the PEC signal is mainly a function of the wall thickness, the conductivity, and the permeability of the material. And the PEC algorithms always assume that the material electromagnetic properties are constant, which means that the only parameters that change should be the wall thickness. So this is an example. So by decreasing the thickness, we increase the decay of the eddy current. So in the black line, we have the near nominal area, and in the orange line, we have a thinner part of the component with a faster decay rate. But of course, the variations of conductivity and permeability uh, may occur, and they will affect the sizing. So to perform the data analysis is always to remember that these the most three important points, which are first to look at the C-scan for area of interest or any special features. Then we look at the PEC signals, so mainly the A-scan, the toe scan, and the Perm toe. And finally, and I could say that it is one of the most important part, is to always use all the information regarding the context to make informed calls. So when we want to assess the indication, it's always important to have in mind what is the footprint and averaging area of the probe we are using. Uh, when we have a defect here that is larger than the averaging area, we will be in a situation where we have a good sizing. So we are located or between plus or minus 10% of the near nominal wall thickness. On the other hand, if the defect is smaller than the averaging area, will undersize the defect, which means that we will have the contribution both of the near nominal wall thickness and the defect in the PEC signal. So to assess the indications, we have access to the toe scans, the computed wall thickness, and the Perm tool. So for the toe scan, its main feature, well, we can describe the toe scan with mainly three parts. The first part is the slope, which contains information about the alloy, either carbon steel or cast iron. The second part is the bending region, which contains information about the defect size. And at the end, the plateau will contain the information regarding the wall thickness or the CDT, which stands for characteristic decay time. So if a defect is larger than the averaging area, you can see that typically the signal or the plateau of the signal will be parallel to the calibration curve in red. On the other hand, if the defect is smaller than the averaging area, you can see that the signal will leave early the calibration, then we'll try to catch the calibration at the end. So in that case, this is typical of a defect that is smaller than the averaging area. And in that case, the indication is a very good candidate to use the computed wall thickness to bring back the sizing to plus or minus 10% of the near nominal wall thickness. So just a summary of how the computed wall thickness works. Actually, we can see that the actual signal is composed of signal coming from both the near nominal in blue and the defect in red. So the tool will extract the information of the defect from the actual signal to bring back the sizing to plus or minus 10% of the near nominal wall thickness. So a few words about the Perm tool. So there's several sources for false positive indication, such as properties, variation, and interfering components. So on the top right, we can see C-scan for both a defect and a false positive. So on the C-scan, both look the same. But if we focus on the false positive indication, we can see typically they will have a stronger signal initially. They will then cross the calibration in red and will also contain a faster decay rate. So all this information will be synthesized in a graph where we have the variation of wall thickness, the y-axis, and the amplitude of the signal in the x-axis. So mainly the information will be summarized with a vector and a trace. So the vector in blue and the trace is in black. And their location in the graph will give us information regarding if the indication is either a true wall loss or possibly a true wall loss or a false positive indication. So I will give you two examples. So the first one is a true wall loss. So as you can see, we have a decrease in the wall loss in the C-scan. So the vector will go toward the negative, well, toward the down, toward the bottom of the graph. And also we see that in that case, we have an increase in liftoff. So we cause a decrease in signal amplitude. So it means that the bottom of the defect will be a little bit, will increase or the distance will increase between the probe a little bit. So it means that the vector will go toward the bottom left. And we can see also in that case that the trace is well correlated with the vector. On the other hand, if we have or a false positive indication, we still have the decrease in wall thickness, so the vector is still going down. But in that case, we have an increase of signal amplitude. So now the vector will go toward the right, so in the dark gray region, which is typically representative of a false positive indication. So if you want to know more about the Perm tool, you can my colleague did a coffee break a few months ago on that topic. So let's move to the data analysis. Oops. So in that case, it is we use a specialized PEC array probe that was specially designed for ship deck inspection. So it has custom 7-channel array. And this probe has a good balance between accuracy and speed with a 178 millimeter of coverage, with a footprint of 18 millimeters and an averaging area of 22 millimeters. Sorry, and with a minimum detectable defect that is slightly smaller than the smaller probe, which is the PEC 025G2. So for in the ship deck, they usually they have a relative they have a relative thin wall, so between 5 and 7 millimeters. They do not have weather jacket, but they have coatings a few millimeters thick, so mainly composed of either coating or tiles. But they contain also several interfering components on the deck or under the deck. So for this presentation, we'll use a ship deck demo plate with representative defect that we manufacture. So on the top, we have on the top left 5 small defects, and on the bottom, we have 3 larger defects. We can see here the defect on the bottom. Here we have a hole close to the defect, which is represent a drain that we encounter on the ship deck. And on the defect of the right, we have a pipe that is welded close to the defect, which is also representative of what we typically encounter in the ship deck inspection. Also, under the ship deck demo plate, we have a stiffener that is welded. So this is what we usually encounter in ship deck inspection. So we have a latent interfering component under the deck. So here on the top left, we have the 4 small defects, which are close to the averaging area or larger, so between wall thickness of 40 up to 90. And we have 3 larger defects on the bottom between 32 wall thickness and 66% wall thickness. And here, this is the location of the stiffener under the plates. They are close to the larger defect on the bottom. I will share now the data. So this is the C-scan that was acquired with the custom 7-channel probe. So the first thing we'll do is we'll go back to the backstage to see the component definition. So as we can see, we have a wall thickness of 6 millimeter, 6.35 to be precise, and with a coating of 3.18 millimeter, which represent the thickness of the tiles. And for typically for a wall thickness of around 6 millimeter, we can expect a characteristic CD time or CDT of around 5 milliseconds. So if we go back to the front stage to the C-scan, so we'll just zoom in a little bit to the content. So we'll just remove the scroll bar there. And as we can see, we have several overspeed. So just overspeed, there is no bad feed or signal distortion. So we'll just remove them. So we'll just remove the warning overlay there. There we go. Then let's go. We'll have a look at the CDT. So we'll go to Setup and PEC Set. There. So as we can see, we have a CDT of 2.5 milliseconds. So it's a little bit lower than the average of 5 milliseconds. So this means that this alloy is pretty fast. If you want to know more about the typical range of the CDT, you can just click on the check mark on the toe scan, and you will have access to all the information regarding the CDT. Now let's move to the advanced setting. We'll now have a look at the averaging. So we have an averaging of 2, and if we look at the C-scan, we can see that it's not too noisy. It's good. So in the case if the C-scan was very noisy, we could always increase the averaging, but it also means that we will have to rescan the component. Now let's look at the gain. So 30 dB. So it's really good. The maximum should be 65 dB. So in that case, it's means that we have a very good signal amplitude. And we have a line filter frequency of 60 Hz. So it was acquired in the lab of Eddyfi. So we are working on a line at 60 Hz. So the line filter is correctly set. So don't forget to change this setting if the line frequency is 50 Hz. Click OK. So let's just have a look of how we acquired the C-scan. Click on scan. So it was acquired from right to left, and from bottom to from top to bottom. So 1 to there. So right to left, top to bottom. Now, before starting the analysis, it is always a good practice to recalibrate over a near nominal area. So we'll just look for a good candidate for that. Say this where, yeah. So on the right side, this is a good place. So I will recalibrate there. So I want to stay away from any special feature overlaps, where in this case we don't have overlaps because we don't have a jacket, any mass effect, edge effect, etc. So this one is a good place. Just click calibration. I will recalibrate there. Great. Okay, now let's see if we have any special feature. So first we can see there we have like a dark line, dark blue line. So as you can see on the toe scan, the signal is going way out of the graph. So this is typical of a mass effect. So this was expected. This is the location of the stiffener under the deck. And this is one of the reasons I did not recalibrate over or close to this region. Now let's look if we have any special feature. So we expect to see defects, a small defect, larger defect on the bottom. But here we have some wall loss that was unexpected. So let's see what we have. So I will use the Perm tool to assess this feature by moving the X and Y direction. And as you can see, this indication as a signature that is typical of a false positive indication. So here the context is very important. So this is a manufactured demo plate, which means that it was manipulated in the shop. So if we look at the shape of this feature, it's like a cylinder, and this is really typical of the use of an electromagnet on a plate. So this is what we are seeing there. So this is the residual magnetization come from the electromagnet. So we must keep that in mind when we will assess the defects. So now let's see the defects. So we expect to see 4 defects. for smaller defects, unfortunately, we see only 3. The fourth one is located right in the false positive indication. So we cannot see it or assess the indication. So the first one, here, the first small one, if we use a Perm tool, you can see that this is clearly a defect there. If we look at the toe scan, yeah, it's almost parallel, but tend to try to catching up the calibration. And actually the size of this defect is close to the diameter of the averaging area. So we could use the computed wall thickness, but we must be careful in that case because we have the mass effect there and maybe some residual magnetization close. So I will just hit here corrosion, we'll compute computed wall thickness. We click OK. So in that case, we have a remaining wall loss of around 40%. It's a little bit oversized, but again, we have, if we close it a little bit, the data selection on the Perm tool, we can see that the Perm tool vector will start from the uncertainty area close to the false positive indication. And if we increase, the vector now goes in the true wall loss area. So, which means that probably that we have a little bit of effect on the change of properties related to the heat affected zone or the manufacturing of the defect. So if we move to the top, we can see now that we have clearly a plateau there. It was expected. So this defect has a diameter much larger than the averaging area. So in that case, we will not use the CWT to assess the indication. Good. So and if we use a Perm tool, we can see that in both directions, the vector points in the true walls area. If we move to the third defect, this one is really interesting. So it's a little bit larger than the averaging area. But again, if I play with the Perm tool, you can see that the vector start from close to the false positive indication or uncertainty, then will slowly goes in the true wall-loss area. So we can see that the trace as this crescent shape form or this crescent shape, and this is typical of a manufactured defects where we have a heat affected zone or change of properties combined with a true wall loss. So it means that an indication can contain both at the same time true wall loss and false positive indication. Now, if we move to the larger area on the bottom left and see that in that case, we have a remaining wall thickness of 40%, which is within plus or minus 10% of the neonominal wall thickness. Now, if we go there, so we expect to see a wall loss of, or a remaining wall thickness of 23%, but we have 50%. So we are well undersizing this defect. Also, we have a hole there. So just remember that we cannot size 0% of the wall thickness. So we will always have a eddy current coming from the nominal or the surrounding of the hole. So that's why we don't have a 0% wall thickness there, but it will affect the PEC signal anyway. This area is much larger than the averaging area, so we'll not use the computed wall thickness in that case. So we'll try to understand why we are undersizing a little bit. So we'll just move to the amplitude view. So we'll go to current view, layout. Sorry, I will split that C-scan in two view. and I will go to the amplitude view. So as you can see, it's very interesting in that case. So as you can see here, the amplitude of that defect is very different from all the other defects. So since the wall thickness, the running wall thickness is quite low, it's mean that it was probably affected or strongly affected by the change of properties related to the manufacturing process. The last defect there located close to the pipe. So this is why we have a zone where we don't have any data. So we did not have access with the probe, which happened quite often for a ship deck inspection because they have a lot of interfering component. In that case, we are sizing close to 68%. So this area is also larger than the averaging area, and we have a good sizing. And as we can see on the amplitude view, this defect it seems that it did not contain any false positive indication, or it was not affected by the manufacturing process. So thank you. Uh, we are now at the. If you have any questions, I'm ready to answer all of them. Uh, the question is, can you catch all the false positive indication with the Perm tool? No. The Perm tool is there to help you to assess if the indication has a typical signature of a true wall loss or a false positive. So it will the indication or the answer or the response of the Perm tool will be true most of the time. But again, if you remember, we need three things to make a call. So we need to take into account the C-scan, the signals, and the context. So it's taking into account the context is always important to do a call. The next question is, can you use the computed wall thickness on a defect located within a false positive indication? No, so to use the computed wall thickness, one of the most important uh, restriction, I would say, is that the defect must be surrounded by near nominal wall thickness. So it's really important. So if we have a defect that is located within a false positive indication, the answer of the computed wall thickness will be inaccurate because it will be strongly affected by the presence of the false positive indication. So next one is, what is the most important aspect of the PEC and VES analysis? Uh, I would say that um, the context again is really important, particularly for the ship deck inspection when you have a lot of interfering component, and that in the example I just presented, we only add one stiffener, but in reality we have several stiffener uh, with several wells, or I would say with several region of containing change of variation of properties, so conductivity and permeability. So it's really important to take into account the context for the advanced analysis. So next one, speaking of the naval industry, is PEX is influenced by the presence of water? No, so actually we have probes that can be deployed underwater. So any material between the probe and the component that is non-conductive will not affect the PEC signal. So you can expect through water, wood, um, any air, of course. Yeah. So next one is any update on the software Perm tool. So the Perm tool was released with the version 2.4 or 16. So up to now, there is no update for the Perm tools. But if you have any questions, yeah, so if you have any more questions, I will be glad to answer them. So just write me at dpicard@eddyfi.com. So thank you for assisting to this coffee break this morning.